So, dear students, uh, here we'll be moving on with some more examples. And you can see we have a normalized wave function, and what we are supposed to do is to find the probability of finding this particle in the region of 0 to L by 2. So the wave function is given here, and this wave function is normalized uh, within the limits 0 to L. Now, now to start with, in order to calculate the probability of finding the particle, so probability of finding the particle, that will be given by psi star, and uh, and in this particular case, the limit within which we have to find this probability is between 0 to L by 2. So, to define the probability in terms of the limits that are given in the problem, what we will have is what I will call it probability of finding particle in the range of 0 to L by 2. That's what it means. So what that will be, that probability will be simply the integral from 0 to L by 2 psi star psi dx. That should be the case here. So the probability of finding the particle, we have to find the probability. What will be the probability of finding the particle of whose normalized wave function is given by this equation? So all I have to do is to take the complex conjugate of the psi that's given. So what I will have, so that probability of finding this particle will be, so if I write down the complex conjugate, so I would call it psi star, and it will be under root of, it's a real number, so there are not going to be any changes in the wave function, and then this probability of finding this particle in the region of 0 to L by 2 will be under root of 2 by L, then sine of pi x by L. Okay, this under root of 2 by L, then sine pi of x by L, and then dx. So this, on evaluating this integral, I'll be able to calculate I'll be able to have the probability of finding this particle between 0 to L by 2. So here we will have 2 by L out, then we will have, the root is gone, so we will have 0 to L by 2. This is sine square pi x by L and dx. So this is the case. So we will use here sine square theta is equal to 1 minus cos 2 theta by 2. So by using this formula, we can find the probability. And what we will have, that will be 2 by L, integral 0 to L by 2. So this is 1 minus cos 2 to pi x by L, and divide by 2. So this 2 and 2 will cancel. I would like to close it, this dx. So moving on from here so what we will have is 1 by L, and here we will have simply for 1 dx we will have x, and that will give us L by 2. and here this integral will come out to be 0, and we can proceed from here if we want. So what will be the integration of this cos theta? That will be minus sine theta, that is sine 2 pi 2 pi x by L divided by the internal derivative of this 2 pi x by L, that will be 2 pi by L. This value should come out to be 0. I had directly used the value of this kind of thing in some previous problem. So here you have the limit, you have to move from 0 to L by 2. Here we have applied the limit. So this is 1 by L times L by 2. Here, okay, we have 1 by 2 pi by L out. So what we have is sine 2 pi x by L minus sine 0. That should be the case. So this is 1 by L, this is L by 2 minus, say this whole thing is x. So this is this will be here L by 2 when you'll give the limits. This 2 and 2 will cancel, and this L and L will cancel, so you'll be left with sine of pi, and this sine of pi, sine of n pi is 0, so this thing is 0 and this thing is 0. So what we are left with, this L and L will go, what we'll get is 1 by 2, so this is 0.5. So the probability of finding this particle from 0 to L, when the wave function that's given there, a normalized wave function was there, that is equal to 1 by 2, that's half. Now let's move on. Let's move on to the next problem that we have. This is our next problem. Now what we have here is that we have a wave function, and what we have to find in this wave function is to find the value of this a. So in order to find a, what I have to do, I have to use the condition of normalization. And then the next important question that's here is where is in case of this wave function that we have for a free particle. This is for free particle, and what will be where the particle will most likely be in the region that's defined. So to solve this problem, what is the first important thing is that I have to calculate this constant, and this is a normalization constant, and I can calculate this using by the condition of normalization. So if I start solving this example, so what is the condition for normalization is integral minus infinity to infinity, then psi star psi dx is equal to 1. Now here I have psi, okay, and what will be its psi star? I should write that first. That will be a star e to the power of minus x squared by 2a, then this will be minus iota kx. So because if you have to take the complex conjugate, you have to change the sign of the iota that's present in the wave function. So what we have to do is that what is given here is 1. Let me call this as 2. I would like to use these two values of wave function, the wave function and its complex conjugate, in this equation, which is the condition for normalization, right? So in doing so, let's move forward. So what we will get here is we will have minus infinity to infinity, and psi star will be a star, and e to the power of, now we can directly see here, this is e to the power of minus x squared by 2. And when you will multiply with this e to the power of minus x squared by 2 a square, they will be added, so 2 will come in the numerator and 2 will cancel, and we will get e to the power of minus x square by a square. That should be the case. Okay, so about the complex part, we can see directly. So this e to the power of minus iota kx and e to the power of plus iota kx, they will give you 1, because these exponents will cancel and you will have value equal to 1. So what's going to happen is that this integral, this normalization condition is boiled down to, so here I will write a, and then I would like to write dx. This is equal to 1. I think that should be clear. All right. So you can check it. You you can see that when you multiply this psi star with psi, e and e will give you minus 2x square by 2a square. Then 2 and this 2 will cancel, and you will be left with what's called as e to the power of minus x square by a square. And then talking about this iota term, this will be cancelled, and you will be able to get the value equal to 1. So from here, we can move on for, now here we will have simply a square. Okay, then we will have this integral minus infinity to infinity e to the power of minus x square by a square dx. This is equal to 1. All right, and the value of this is a standard integral, and there is a need of separate integration that's to be done. But as long as the physics point of view is concerned, we can directly use the value for this standard integral minus infinity to infinity e to the power of minus x square a square dx, and its value is it is a under root of pi. So this is a square a under root of pi is equal to 1. So from this equation, we can have the value of a square, and that a square will be 1 by under root of pi. So a is 1 by a under root of pi. That should be the case. So when square will transform, what we will have is we will have 1 by a to the power of 1 by 2 and pi to the power of 1 by 4. So this will be the value for our normalization constant that we have in the original wave function. So now the question is so we can write down that equation in terms of this normalized wave function, where we have calculated the value for normalization. And here, what should we do is that this wave function psi of x is now, it is 1 by a to the power of 1 by 2 under root of pi raised power 1 by 2. Can go like this. And then we have e to the power of minus x square by 2a square plus iota kx. Now, the probability density, if we have to talk about the probability density, so what we have to do for that, for probability density, what we have to do is to have psi star psi. And when we will do that, what will we obtain from that is we have to take psi of x whole square. That should be the case. Now, when we do that, so we will have the square of everything that we have here, and this will be 1 by a to the power of 1 by 2. Then we have under root of pi, then raised power 1 by 2, okay, and then we will have the square of this, okay, then we will have square of e to the power of minus x square by 2a square, then we have into e to the power of iota kx whole square. This will be the case. Okay, so from here, what we will get is this square will cancel with this root, so we will have 1 by a. This square will cancel with this root, we'll have root pi, and this square will go into a to the power of n raised power m. That will cancel this 2 and 2. What I'll get is e to the power of minus x square a square. And the other part, the other part that you will have here will be that will be over. So this will be the final. This will be the final expression that we will get for psi star psi. Now, what does this equation tell us? This equation tells me that that the probability is maximum. The probability is maximum for x is equal to 0. Okay, so that the value for this psi star will be automatically 0, and it decreases, and it is going to decrease for if I take the magnitude of this x greater than a here. Okay, so in that case, the exponential function is going to decrease. Thus, what we conclude here is that we conclude that the particle is most likely to be found within the region of width a. This is the region where the probability of finding this particle is maximum on the either side. So if this is the origin at x is equal to 0, here the probability is maximum, and then you will have decreasing exponential probability towards plus a. Then you will have decreased probability in the other side of x is equal to a. So this is what the solution that we have obtained from this probability density, and we understand it from the very first point of view that if we have to multiply a function with its complex conjugate, you will always come up with a real number. That's why I didn't turn up to calculate it, because it will directly give you the value equal to the whole value of this will be 1, so that the final result that we'll have for the probability density of finding the particle will be equal to this.